Okay, so we already understand that continuous random variables are continuous, right? There's no gaps in between. And here's the thing. This isn't a rule, but it is a very interesting relationship between them. For discrete random variables, a lot of our measures are found by adding up things. For example, the mean, you find it by taking each outcome and the probability of each outcome, right? And then adding all the outcomes up, and that's the mean. In the case of a continuous random variable, you don't have individual outcomes, right? So you can't really add where there's no individual outcomes, right? So in that case, when you have to add an infinite amount of something that isn't actually real or doesn't actually have a size, how do you treat that mathematically? You have to add an infinite amount of things, but those things actually don't have a real size or real gaps in between them. Oh, I see what I'm writing.
It's not writing anything at the moment.
Oh yeah, I'm not writing anything. Do you see my pen?
An integral?
Can you say that again?
Integral?
Yeah, that's true. Integral. So, I think the error is on your side. The problem is on your side. Asafa, I think you may want to log out and log in because I am showing my screen.
Check the chat.
Yeah, other online students, do you see what I have? It could be a problem on my side as well. Yes? Okay. Good, good. So, just like Milton said, right, in the case of a continuous random variable, since we can't really add an infinite number of things, we have to integrate. I mean, that is what an integral is, right? You take an infinite number of differentially or infinitesimally small elements, you add them up, that is what an integral is. And this isn't a rule, but it is there so that whenever we have to calculate something in a continuous random variable, we could probably be able to use the same expression from a discrete random variable and then just like integrate instead of add. We could, who knows, but we'll see. So let's talk a little bit about the differences between continuous and discrete random variables. For discrete random variables, we said that there was a function that gave you the probability of each outcome, and that function is called the probability mass function, or PMF. Is that correct? Yes, probability mass function, good. For continuous random variables, we no longer have that function because we say that for continuous random variables, you can't really find the probability of one outcome. You can't. You can only work on ranges. So because you can't find the probability of any one outcome, instead of dealing with probability mass functions, we're going to have to deal with probability density functions. So when we deal with probability density functions, the idea is we're not really looking, right, at the probability of one outcome. So this probability density function, which unfortunately is also called little f of x, but here, when it's a probability density function, or PDF, this f of x is not going to give me a probability. Instead, it's going to give me a probability density. In other words, it's going to give me a value that I can then use to find the probability over an interval. And I'll explain how we find the probabilities in just a second. Now, just like the probability mass function, the probability density function also has to satisfy a couple of different properties. One such property is that the probability density function always has to be greater than or equal to 0. The other property is that if we were to add up, and when I say add, since it's continuous, we actually integrate, but if we were to add up all of the values inside the probability density function, we would get 1, similar to a PMF, right? And finally, and here's where things start to diverge a little bit, the probability that my random variable falls within an interval. Let's say we want the probability that x lies somewhere between a and b, can be found, okay, by integrating your probability density function from a to b. So those are the three properties of probability density functions. So you can kind of see that it's not really an actual probability value that spits out. Instead, you spit out the probability of a range of values. So you still have to integrate, and that's the important thing. When you integrate from negative infinity to infinity, all you're doing is you're taking that function and you're integrating over everything. And that should include the entire sample space, and therefore that's why it gives me 1. Okay? So this is the probability of the entire sample space, right? And this is a finite probability over a region, a small interval within that sample space. So that is a probability density function. I think it's a lot better to understand it a little bit graphically, so let me explain. Let me just give a quick example. Let's say we have a uniform probability density function, where this is f of x, and this is just x. So if it's uniform, we should have the same probability density for the entire, for any value of x. And what we're saying here, if my sample space goes from 0 to 5, then this, and this is my probability density function, then this graph is going to represent my sample space. And the idea is that the area that you calculate as you integrate, right? You know, integral area under a curve, right? The area that you calculate is your probability. For example, if I want to find the probability that my value lies, maybe let's say between 1 and 2, I can take this area, and that area will be my probability that my value lies between 1 and 2. However, if I want to find the probability of the entire sample space, then I have to integrate from 0 to 5, or in this case from negative infinity to infinity, right? Because from negative infinity to 0, my area is 0, and then from 5 to infinity, my area is also 0, right? So we integrate from negative infinity to infinity, it's the same as integrating from 0 to 5, right? Because before 0, there is nothing, right? There's no area to add. After 5, there's nothing. There's no area to add. If we're integrating over the entire sample space, we get the probability that your outcome will be somewhere within the sample space. And you already know that the probability of a sample space is what? The probability that your outcome is in the sample space. Yeah, it's 1, right? The outcome has to be the sample space because by definition, my sample space is my outcome. Thank you, Carlos. Not you, the other Carlos. Yeah, that's correct. So for continuous random variables, we may benefit from trying to look at these in a more graphical, visual way, rather than just by numbers. Now, we'll still use numbers, math, to calculate everything, but if we can understand how this works visually, it'll be much easier time, like going over or finding the different probability values. So, just to give a couple of definitions and measures before we start working directly into an example. I want to talk a little bit about the cumulative distribution function. You know, we call that CDF. For a discrete random variable, my cumulative distribution, you may remember, was just taking the probability of each value plus all the values before it, right? That's what we did for cumulative. We just took a probability of value, and then we added all the values before it. For a continuous random variable, the cumulative distribution is the same. You're still adding all the values before it. However, because now it's an infinite number of values, instead of adding, what do? You integrate, right? And that's the idea. For a cumulative distribution function, we're taking this PDF, but for every value, we will include the cumulative distribution function of that value plus everything that came before it. So essentially what I'm doing is I am integrating from negative infinity to your value, and that is my cumulative distribution. We actually call this cumulative distribution big F, which I think we also call it for discrete random variables. It's the same. And remember, that gives me the probability that my random variable is less than or equal to some value. Now here, it works, right? Because here we're saying the probability that your value is in a range. And because it has an interval, a clear interval, then that gives me an actual probability. Now, there is a relationship between the two. You can see that big F, my cumulative distribution function, is the integral of little f. And that should give us some clues, right? If you think of the fundamental theorem of calculus, how can we relate big F and little f? First of all, what's the fundamental theorem of calculus? You've never heard of the fundamental theorem of calculus?
We have heard of it.
Awesome. The fundamental theorem of calculus, if I can remember it correctly, tells me that the integral of a function is also equal to the antiderivative of that function, right, evaluated at the 2 points of the integral. In other words, have you ever noticed when you have an equation and you want to integrate it, you don't draw the equation and then calculate the area, you just take the derivative, right? Why is that? Because of the fundamental theorem of calculus. Did that involve partial derivatives? Actually, it doesn't have to involve partial derivatives. Because fundamental theorem of calculus it's actually the foundation for the rest of calculus, and partial derivatives are like a small function of it. Yes, it has been a while for me as well. I understand, I perfectly understand. So the idea is that the fundamental theorem of calculus tells me that the integral of a function is also the same as the antiderivative of that function, right, plus a constant, or evaluated over an interval. So if that's the case, we can take this information and we can rearrange it to say that my probability density function is equal to the derivative of the cumulative distribution, right? I think we can say that, right? Because we say that the cumulative distribution is the integral of the probability density function. Therefore, the probability density function should be, right, the derivative of the cumulative distribution function. This will not be as important in this class as it is in other statistics classes, but because you'll notice that most statistics classes, like Stats 101 or something, they're actually pre-calculus, like before calculus or during calculus, so this doesn't really become that important, but it will be a helpful tool because sometimes you can use this to convert between the two, especially if you already have a clear equation for your probability density function or for your cumulative distribution function. So, in this case, right, we can kind of tell that for continuous random variables, we may end up dealing with fixed equations rather than just like tables of probability distributions, right? So it looks like we're going to be dealing with equations. I mean, we have been dealing with equations before, but these equations are kind of finite, they're discrete. It's pretty, they focus on only on discrete values. This one, we're going to be dealing with continuous equations. Now, because we're going to be dealing with continuous equations, I think it's important that we get the measures out of the way, that we understand how to find measures for continuous random variables. So I will start by finding the mean. This was easy. And let's try to think a little bit. For a discrete random variable, the mean was equal to the outcome, x, right, times the PMF, right? So x times f of x, and then you just add all of them up. So how do you think the mean would look like for a continuous random variable? For a discrete random variable, you have x times f of x, and then you just added all those values up. So for a continuous variable, what? Okay, but what would that range include? Remember the general quote rule unquote, right? Wherever we add, we integrate, right? So how do you think the mean would look like in a continuous random variable? Exactly, that's correct, Renee, on the chat. X times f of x will be integrated, will be the integrand, integrated, right, over infinity, right, over the entire sample space. That's absolutely right, right? In a discrete random variable, we had x times f of x, and we just added all of them up. But here, because it's a range, instead of adding, we're actually integrating. And we're integrating x times the probability density function. Remember, this now is no longer my probability, it's my probability density, because we can't actually find probabilities for individual values of x. What we can find is probability density. Okay, good, that's absolutely right. Following on our definition of variance for a discrete random variable, what do you think the variance would look like for a continuous random variable? And yes. How do we find variance in the first place for discrete random variables? For discrete, just the general, not for any particular distribution, just in the general equation for variance. What was that like? You're gonna have this handy if you're gonna take a test this week. Just give you a heads up. This needs to be handy. Online students, you can't see me, but I'm sitting down because my back hurts. So in the chat, we have, if it's x minus mean squared times f of x, then it's the same, integrate over infinity, right? Yep, and that's true. It's the same equation that we have for discrete. And remember, it's going to be x minus mean squared times f of x, exactly the same equation, but now we are integrating that over the entire sample space. That's absolutely right. Good. I'm going to give you a simple one, and I hope that you can answer this one for my own sake, for my own well-being. What would the standard deviation be?
Square root of the variance.
Thank God. Yes, it is. Thank you. Good, and that's right. So those are my three measures. So you'll notice that the equation actually looks the same, except that instead of adding, now we are integrating. So that should give you a bit of peace of mind here in that, okay, we don't have to memorize new equations. In fact, you don't have to memorize any equation, but we don't have to memorize new equations. It's actually the same, but it's of adding and integrating. My advice would be that you include all this in your little table of values, because it may be helpful to have not just discrete, but continuous random variables in there as well, in case you need them for, I don't know, some assessment like a test or something. I don't know. Okay, so that's a general introduction, right, to our continuous random variables. Now, what we're going to do now, just like what we've been doing in the previous classes, is just go over some of the general, some of the very basic types of continuous probability distributions. I think the plan for today is to talk about the uniform distribution, to talk about the uniform distribution, and then maybe give an example or two. But of course, there are other probability distributions that we are going to be covering next week. But just to give you a little bit of peace of mind, the exam will cover up until the material in the notes for today, which we're going to finish pretty soon, and we may exceed a little bit, but the exam won't cover anything that we go over the notes. Okay? Just hopefully give you a little bit of peace of mind. I'm looking over my notes for next week. So next week, we're supposed to start directly with the normal distribution, and that's a really interesting topic that, I don't know, I feel like it does deserve its own class. So let's see how far we get today, and then we'll decide how the calendar is going to may or may not change. It may not change, but let's see how far we can get to today at first. The first thing I would like to talk about is the simplest type of continuous probability distribution, and that is continuous uniform distribution. Look at that name, continuous uniform distribution, and then tell me this, what characterizes this type of distribution?
It's all the same.
Sorry?
It's all the same.
It's all the same. If I were to graph it, what would that graph look like?
Straight line.
Horizontal line, correct. That's absolutely right. And that's completely right? That's a continuous uniform distribution. What uniform tells me, right, is that the probability, or in this case, the probability density, should be consistent, should be constant throughout the entire range. But of course, it's continuous. It's no longer discrete. So now instead of dealing with individual outcomes, we have to deal with ranges. And because we have to deal with ranges, okay, then we need to do a little bit of, a little bit of math here when we're integrating and finding the measures and all that stuff, okay? The probability density function of a continuous uniform distribution, okay, will actually depend on the range of that distribution. So if we remember what a uniform distribution looked like for discrete, so we'll just recall here, a discrete uniform distribution. You have your little tables that I recommended to use for the exam. What was the PMF, the probability mass function, for a discrete uniform distribution?
1 over n.
1 over n, right? So we said that basically the probability of each outcome in a discrete uniform distribution depended on the number of outcomes you had. You flip a coin, 2 outcomes, so the probability is 50-50, right? 50%. But you roll a die, that's 6 outcomes, so the probability of each outcome is 1 over 6, a little smaller. If you have 10 outcomes, your probability is only 10%. So the number of outcomes determines that probability. For a continuous uniform distribution, it can't really be the number of outcomes because there's infinite outcomes. Instead, it's the range of those outcomes. That's what determines what your probability mass function is going to look like. Now, the way I initially had this in the notes is just to give you the PDF here, the probability density function, the mean and the variance. Let's try going over this a different route. Let's try looking at the graphical approach, which I think is a little bit more helpful in terms of understanding what this looks like. I am going to graph a continuous distribution. And let's say that my sample space ranges from A to B. So this is x. This is my probability density function, f of x. From A to B. If I were to just graph it, just eyeball it, what would my graph look like again?
Horizontal.
Throughout the entire line, like forever?
A to B.
From A to B, right? My sample space ranges from A to B, so my probability density function will be a horizontal line from A to B, and everywhere else will be 0, right? Because there is no, there's no sample space everywhere else. Good. So we know this much. We know that I can plot it, I can graph it, and my continuous uniform distribution, in this case, will be just a horizontal line that ranges throughout my entire sample space from A to B. Now here's a question. If we know the range, if we know A and B, do you think it's possible to figure out where this line is? Like if it's here, 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 do you think it's possible to find that value of the probability density function? The answer is yes.
Yes.
Yes, okay, yeah, good. But then let's see if we can tell how to find it. So let's use a little bit of critical thinking here. This is my sample space. I'm going to draw like a little square on it. What is the probability that my outcome, right, the outcome of my experiment falls within the range of the sample space? 1, right? Good. So if I take this entire area Because we know, we already said that the area under PDF, right, the integral is your probability. So if I take this area, which is just the same as integrating, right? This is the same as integrating from a to b, or even from negative infinity to infinity, because it's just zero, it doesn't add anything to it. My PDF. Or it's also the same as taking the area, but we know that it's equal to 1. Now what shape is that? Let's just be more general.
Rectangle.
Rectangle, good. So is there any way to geometrically find the area of that rectangle? Okay, so what's the area of that rectangle? What's the area of any rectangle? Base times height. What's my base? Use a little bit more mathy terms. A to b, but
B minus A.
b minus a. Good. So we know the base of this rectangle is b minus a. What's the height of my rectangle? What is this value? What's this line? F of x, good. So taking what you know from geometry, if I take b minus a and I multiply it by f of x, I get the area of this rectangle, which is? What's the area of this rectangle? Somebody said
No, 1.
1, right? It's the sample space. The area is 1. Good. Therefore, can I write down my probability density function as a function of a and b?
Should be, yes.
And it's?
Yeah.
Okay, what is it?
So 1 over b minus a.
There we go, good. 1 over b minus a. So as long as I know the range, I know the PDF, I know the probability density function. For any continuous uniform distribution, the probability density function is 1 over the range, or 1 over b minus a. That is absolutely right. Great job. Really good job. Good. Does that make sense so far? I do want to use this graphical approach because it is, I would say it's a little bit helpful, and it will definitely help when the shapes start to get a little bit more complex. It'll help to be able to see this in the form of areas and graphs and geometry. I like geometry, but it'll be very helpful to see this in the form of geometry. Good. So that is a continuous uniform distribution. Now, if I want to find the probability in a range, all I have to do is integrate this equation over a range. But there's actually a constant, right? So all I really have to do is multiply this times that range. That's all I'm doing. Okay? Let's see if we can figure out the measures of a continuous uniform distribution. First measure we always try to find is the mean. And we already said a little bit earlier that the mean was just the integral of x times f of x dx. So there's two different ways we can find the mean. We can integrate it, or we can do the geometric approach. We have time, let's do both. We know the mean is the integral from negative infinity to infinity, but this is the same as saying from a to b, right? Because it's from negative infinity to a, there's nothing. From b to infinity, there's nothing. So this is the integral from a to b of x times f of x dx. Now, f of x seems to me that it's a constant. It's 1 over b minus a. B minus a doesn't change, right? So it's a constant. So what can we do with a constant here?
Bring it outside of the.
Okay, take it outside of the integral. Good. So let's go ahead and do that. I'm going to get f of x, which is 1 over b minus a. And now what I have here is the integral from a to b of x times dx. I think this looks solvable. I hope, right? So what is that integral equal to? Or at least give me the steps, not the whole answer. Okay, yeah, 1 over half x, good. So what I get here is 1/2 x squared evaluated from a to b. Is that correct? Yeah. This would be, let's see, b squared, right, minus a squared divided by 2 times b minus a. Is that correct? So far, am I good? Am I integrating correctly? I took calculus a long time ago, so. All right, that looks correct. Let's do a little bit of math here. B squared minus a squared. Is there another way to rewrite that so we can get rid of the exponents?
B minus A in parentheses.
B minus a. And
B plus A. Yeah, B minus A.
times, I think you said it, or somebody said it. B plus a, good. Right, b minus a times b plus a gives you b squared minus a squared. Good. And all that's divided by 2 b minus a. Oh, well, you look at that. Looks like b minus a and b minus a cancel out. And what this gives me is that the mean is just b plus a over 2, which is the average between b and a, right? So far, so good, right? Okay, so we found the mean. Good job. I'm going to write it up here. The mean for a continuous uniform distribution is b plus a over 2. Now, the thing is that, yes, that is the quote correct unquote approach, but we could still probably figure this out graphically without the need to go over these steps. Let's be honest, half of you did not remember this relationship, and that's okay. So let's see if we can figure this out graphically. What does the mean tell me? Like, what is the mean? Like, conceptually speaking, what does it mean? I think we had to talk about this like in the last class where we went over different versions of what the mean was, but like, what does it mean? What is it? If somebody says, hey, I'll give you $1,000, you can tell me what the mean is, that I can understand. And the person is an arts major or something.
An average.
What?
Average.
And what does that mean?
It's the general representation of the group.
Okay, general representation. I like that. I like that. What does that tell me about the values, the overall distribution of values?
They tend towards that particular value.
Can you say that again?
They tend towards that particular value.
Can you say that louder so the online students can hear you?
The value that the data set tends towards.
Exactly, right? Your values tend towards that value, right? So if all my values are tending towards the mean, let's think about it. If my values tend towards the mean, in this case, what this is telling me is that my values must be trying to go towards a mean. Okay, they tend towards a mean. Now, there's something interesting about a mean, especially when it comes to continuous uniform distributions. If my values are tending towards the mean, that means that behind my mean, I should have half of my values trying to go there. In front of my mean, I should have the other half, right? Because that's exactly what's happening. Like, my values are tending towards the mean. If my mean were here, I actually have more values here and less values here, so they're not actually tending towards the mean. In order for my values to tend towards the mean, my mean has to be at a place where half of my outcomes are on one side, half of my outcomes are on the other side, at least in terms of probability. Okay? Can you say that again?
In the middle.
Okay, and what is the middle, or let's not call it the middle, because future graphs will be more complicated. The centroid, I think, is a better word, the centroid. That place where if you were to balance this cube, you would have half of that volume on one side, half of the volume on the other. So if we were to find the centroid of this cube, the point where half of the values are on one side, half are on the other, what is that centroid in terms of A and B?
A plus B minus A over 2.
Yes. Well, yeah, A plus B minus A over 2. Okay, yeah. Or just B plus C over 2, right? Because it just cancels these. Good. So this is simply the midpoint between A and B. That's all it is, the average of A and B. So you can find this graphically. You can find this by integrating. You choose whatever method works best for you, right? But I think it's very important to understand this graphically, because let's say, and this is not really going to happen, but let's just, for the sake of this example, let's say that I give you a probability distribution that looks like a triangle. And I want you to find the mean, and you forgot to write down the equation for the mean of a triangular distribution. Again, that doesn't exist. I'm just saying that, let's say you forgot to find it, what can you do to find that mean? If you don't have the equation with you.
Find central.
Find center of a triangle, right? Center of a triangle is located at 2/3 from the short side or 1/3 from the long side. So as long as you have this value and this value, you can find the mean. Yeah. So that's why it's important to have this graphical approach, because it'll help you understand, or at least even study, probability distributions that are, not even that you haven't even seen before, right? If you understand it from a graphical perspective. We're missing two more measures, the variance and the standard deviation. Of course, standard deviation is just the square root of variance. But let's look at the variance as well. Now, this one's a little bit, there's a little bit more work involved, so I'm not going to go through the entire integral. But if you do try to integrate, you will find that the variance is going to be b minus a squared over 12. It's going to be relatively simple, right? You get x minus mu. In this case, mu here is just b plus a over 2. And you multiply that by 1 over b minus a. 1 over b minus a is actually a constant. You can take it out. X plus mu, because it's elevated to the power of 2, then you can't really take it out of the integral. But integrating that is actually not that complicated. But anyway, your final result is going to be b minus a squared divided by 2. That's your variance. And of course, your standard deviation is what, Carlos?
Square root of 2.
Oops. Yeah, you're absolutely right. There we go. Fix it. Yeah, that's absolutely right. Good. So this is the simplest form of continuous probability distribution, the continuous uniform distribution. Of course, in the future, the others will start to get more complicated. I don't want to end the class until we actually do at least one example. So let's do one example before we end today's class. And like I said, thinking about it, I don't think we should start normal distribution until you have the notes, because this is a bit of a heavier topic and also an important one in terms of this is the most important probability distribution you're going to look at. I don't want to spoil it by forcing you to learn something without actually preparing the materials for it ahead of time. So let's wrap up after this example, and that's going to be the length of the exam. Again, we may not have everything in the exam. I'll just fit in what I can fit in. Actually, I've already done it, so I tried to fit in what I could fit in. but it's going to be somewhere amongst the material that we've covered. And that kind of forces you to kind of study everything, right? This is an example also from the book, just like all the other examples this week. And this is the example of a uniform current. Pretty simple example. Let's say that X is the current measured in a thin copper wire. So my random variable is the current which is measured in a thin copper wire. And let's assume that that measurement, that current, ranges from 4.9 to 5.1. So X will stand somewhere between 4.9 and 5.1. I would like to know the probability that my current is between 4.95 and 5 flat. Okay, so we're measuring current in a copper wire, and the current in that wire is uniform. And we know that our measurements could vary between 4.9 and 5.1. What I'm saying here is that my sample space, or my random variable, which in this case is my sample space, lies somewhere between 4.9 and 5.1. It can be any number between 4.9 and 5.1. But now I would like to know what is the probability that my measurement of a current is between 4.95 and 5. Any ideas on how we can start this one? What do we need here? What's the first thing we need? We're looking for a probability, right? So is there mainly a function that I can use to find the probability?
Cumulative distribution.
I don't want to use a cumulative, that's too much. Is there any other type of function? Is there any function that every single probability distribution has per single curve when we talk about probability distributions?
X,
What?
the function, the f of x.
Yes, right, the probability density function.
Yeah.
That's correct. The PDF, that's correct, Renee, as well. Yep. We want to find the PDF, the probability density function for this system. But I didn't give you that. Is it possible to find the probability density function if I'm telling you that it's uniform and I'm telling you the range of current? What is the PDF?
What would be what I say?
Yep, 1 over B minus A. What's B, what's A?
D would be 5. A would be 4.05.
B is 5.1.
0.2.
All right. I'm hearing different things from different people.
B minus.
It's 0.05, right? Because b minus a,
Is it really?
5 minus 4.95.
So, okay,
Or is it?
I think we're not understanding here a little bit. So, if we look at our example, this is the entire sample space.
Yeah. I was gonna say.
Okay,
So-
B and A are the limits of my entire sample space. Not the interval that I'm trying to study, the entire thing. So Milton, what's B and A, what's A?
5.1 and 4.9. Yeah.
There we go, 5.1 and 4.9. Good, good. So that gives me a probability, what do you call it? A probability density function of what?
5.
5?
Yep.
Okay. Good. We found a probability density function. But now what I want is to find the probability that my random variable, that my current lies somewhere in this interval. Okay? So what can I do? Well, I know that probability of x being between, let's say, 4.95 and 5 is going to be the integral from 4.95 to 5 of my probability density function. And what does that give me? Well, we know that f of x is a constant, right? Is it?
Yeah.
Okay, so we can take it out. I'm going to take out that constant, which is 5. And I'm just left with the integral from 4.95 to 5 of dx. So how much is that?
Is it 0.25?
0.25?
Yes.
Okay, so we have 5, right? Multiplied by 5 minus 4.95.
Okay.
So that's 5 times 0.05, right? Okay, so it's 0.1.
5. Yeah, 0.
There we go. Good. So 25% is my chance, is my probability. Good. Not bad. You can solve it this way. We can also go with the graphical approach, where we have already found f of x. We know that it's 5. And we just have to draw this little square, right? We know that this is 5. We know that this is 5.1 minus 4.9. Let's suppose 4.9 and 5.1. But now what we're looking for is only the area of a rectangle that lies between 4.95 and 5. And what's the area of this rectangle? Well, the area of a rectangle is just base, so 5 minus 4.95 times height, which is 5. And you'll see that you land at the same thing. So you can solve it whichever way is best for you. On the exam, are you going to specifically ask for graphical, or is it up to us, whichever one we want to do? Normally, I don't specifically ask for a method. So you can use whichever one you find easiest or better. Even though I'm not going to ask specifically, I could, for example, give you nothing but a graph. And in that case, it's kind of easier to just do a graphical. Or I could just give you a straight out equation. So I'm not going to ask for one. You can do whatever you want. But you can work with the data you have. In both cases, you get exactly the same answer of 25%. And that's it. That's pretty much the continuous uniform distribution. Are there Any questions? And I'm wondering why it's not hearing the chat here. Like normally it should make a noise whenever somebody types in the chat. But anyway, are there any questions? Awesome. If there are no questions, then we can continue on Monday.